In any case, what you guys didn't see there apparently was our, just a very, very brief description of what we have already known for a long time, maybe phrased in terms of three-dimensional descriptions. But other than that, we've been doing it for a long time. Here's the new kind of description. Our description, so we've got two particles, and we're going to say, we'll call them particle 1 and particle 2. And we're going to describe the position of particle 1 with a triplet of coordinates, say x1, y1, and z1. We'll just put those together and call them r1. So that's for particle 1. And the location of particle 2, or the spatial variables associated with particle 2, because it's not necessarily localized, we'll call r2. And our complete description of the two-particle system is going to be some wave function, some function of r1, r2, and t. Of course, it can change with time. And how do we get these descriptions? Well, they got to satisfy the time-dependent Schrodinger equation, which now has to be a little bit different because our Hamiltonians we were specifying before were specific to single particle states. So our new Hamiltonian has a kinetic energy term for particle 1. This del squared only refers to particle 1 variables. So it's, d squared dx1 squared plus d squared dx1 squared plus d squared dy1 squared, and so on, right? Same thing over here. We have a kinetic energy operator term for particle 2. And then we've got some potential energy, which, depends in general on the locations of particle 1, particle 2, and time. And it might depend on the separation of particle 1 and particle 2, right? If particle 1 and particle 2 are an electron and maybe 2 electrons, there might be some repulsion, electrical repulsion between the two, and that's going to affect that potential energy function. Very quickly, we're going to, again, ignore the time dependence there and say the potential isn't just randomly changing with time. It depends on the positions of the particles, but it doesn't change with time, although you could consider those kinds of cases. So how to solve this differential equation, which now, oh my gosh, it's a partial differential equation with 7 variables in it, right? x1, y1, z1, x2, y2, z2, and t. So all those partial derivatives are in there. Well, in order to tame the beast a little bit, we're going to look for separable solutions. In other words, product solutions, solutions that are a product of a function of spatial variables and a function of time variables. And it's the separation of variables works exactly the same way, and the time factor works exactly the same way. So we find out when we separate variables, it's not worth going through again, but you can do it yourself, or I'm not sure to what degree it's spelled out in Griffiths, but you can try it yourself. The separable state is a product of a function of spatial variables, which has to satisfy the time-independent Schrodinger equation, same h with the same 2 kinetic energy terms in it there. H psi e equals E psi e, where these psi e's are only functions of spatial variables. And then you've got the corresponding time term. And in the same way as before, the collection of all those special separable solutions, the solutions to the time-independent Schrodinger equations, form a complete, and they can be made into an orthonormal set. So the complete orthonormal set, and that means that an arbitrary function at, say, at time t equals 0, an arbitrary function of those 2 spatial variables can be written as a linear combination of the separable solutions, and here we're just writing it out at time t equals 0. And if I want to put the t in there, I just put the corresponding e to the minus et over h bar term in over there. So same exact stuff as before. How does psi relate to observations? Well, again, there's a probability density associated with it, with the magnitude squared of the wave function as a function of time. That gives me the probability density as a function of R1, R2, and T. So that's 7 variables if you're in 3 dimensions. Well, okay, if you're in 1 dimension, it's only 3 variables. Still kind of confusing, but that's the case that we'll look at quite a bit to try to get some intuition about this, right? And so we've got to do an integral. at a particular time, we can integrate over a spatial region of R1 and R2 to find the probability of measuring particle 1 in that region of R1 and particle 2 in that region of R2. We've got to put appropriate limits on there. So just to, I know that's, especially if you haven't done the reading, that's a lot. Let's think about that in problem 1 here. I'm giving you in problem 1, and for those of you on Zoom, this is under worksheet for today's class under today's date. I'm giving you a particular psi of x1 and x2 at time t equals 0. And our goal is just to think about this particular one. I mean, just to kind of think of functions of these two variables. And what I want you to do in the axes on the right is sketch what psi looks like at time t equals 0. Now, how do we do that? It's hard to sketch it because we need 3 dimensions to do a normal plot of a function. But here, you could kind of do it for level curves. So if, let me unshare the screen now. In this plane, you know, you could sort of say, oh, here's x1, here's x2. These are particles confined to 1 dimension. So we don't have y's and z's here, right? You know, I might say, well, if I'm plotting what psi is as a function of x1 and x2, maybe it's really large here. And so I've got some level curves that look like that. So maybe here's where it's really positive. And then over here, perhaps it's really negative. Something like that, right? So going down to the bottom of a valley there, up at the top of a hill there, that kind of thing. So don't worry too much about the details of your level curves. I'm not expecting something that MATLAB would spit out, but rather just think about where in the x1, x2 plane is this function going to be maximal. I think that's pretty easy to figure out by looking at the function. Notice there's an x1 minus 2 squared and an x2 plus 2 squared. That's on purpose. One of them has a minus 2 and one has a plus 2. And then in the next one, you're going to plot the probability density as a function of x1 and x2. That's just the magnitude squared of that, and try to indicate where in space the probability density is going to be largest. And once you get a very, very rough sketch, just so we know where the peaks and valleys of the function are, then try to answer the questions in C. I'm assuming A is chosen so that it's normalized. Okay, help me sketch the picture just very, very roughly here of what psi looks like. I'm going to try to draw some level curves, not thinking about it too much, just where does it look like the tops of the mountains and the bottoms of the valleys are. Psi of x1, x2. So it's a product of these two Gaussian functions. Where's the peak of the probability density going to be at? Where in the x1, x2 plane? Right. I mean, I just look, well, it's a product of a function of x1 and x2. And so the claim was that when, when x1 equals 2 and x2 equals -2, that's down here, then the height of our function is a, and that's the biggest it ever gets, right? And then, it's a product of two Gaussian functions, not so too surprising that that looks like a Gaussian in 2 dimensions, right? So it's gonna look like a hill that falls off, like a Gaussian function in all directions. So it's gonna go down and down and down right there. So it's maximum positive here, and it never gets negative. Psi certainly could get negative, but I just made up this function. It happens to asymptotically go to 0. So very quickly, it's heading off down to 0 everywhere else in the plane and reaching the top of a mountain peak right there. We could draw it in a 3D kind of view of a surface of the function, but that's kind of harder to do. In B, how is rho going to look different than this function? Where's rho going to be maximum? Yeah, I mean, it's going to be, it might have looked really, if it were negative, it certainly wouldn't be negative because we're taking the magnitude squared. But for this particular function, rho and psi kind of look superficially the same. They are different because one is the square of the other one. But, the maximum of rho, which is the magnitude of psi squared, is going to have a maximum of whatever that normalization constant is squared, and it's going to fall off. It will fall off more quickly because it's the square of a Gaussian function, but other than that, it's maximal at the same place. Okay, so no big difference. Those will be different in other problems that we're going to work out below, but for this case, it's not so different. Okay, C, where near which x value is particle 1 most likely to be found? So this is supposed to be telling me if you make a measurement of the position of particle 1 and the position of particle 2, what the probability density is at different regions of that plane. And the claim is, well, this function is very large near x1 equals 2 and x2 equals -2. So that means I'm really likely to find x1 near x equals 2. Right? So the answer to the first question in C is 2. Does your answer to this question depend on where particle 2 is found? In other words, suppose I said, I know it's unlikely, but particle 2 was actually found up here, at x2 equals 0. Does that, is that going to affect my answer to where x1 is most likely to be found? In other words, do you need the information about where particle 2 is found to find out where particle 1 is found? No, they're sort of independent of each other, right? Both, I could say, look, just looking at this function, particle 1 is most likely to be near 2. Particle 2 is most likely to be near -2. We're going to find out that's usually not the case. So this is kind of a special state that we're talking about here. But in this case, it sort of appeals to our intuition. We can say, it's like particle 1 is in a state that's localized around 2, and particle 2 is in a state that's localized around -2. Does the location where particle 1 is found affect where particle 2 is most likely to be found? Again, no in this case, right? Even if I get a really unlikely value for x1, x2 is still going to be most likely to be found near -2. So those two kind of don't depend on each other in this case. I know that's not that exciting, but find out that generically that's not the case. So that's to be compared with something to come. Any questions on that? All right, let's go back here. And oops, there we go. So I want to address the question, which my memory is that Griffiths makes some mention of this in the book too. For a particular state, does it make any sense to say particle 1 is in a particular state? To say it's in a particular state, maybe I could say, I know something about the probability distribution of particle 1 independent of particle 2. In other words, I don't care where I find particle 2. I can tell you where particle 1 is most likely to be found and least likely to be found, and I don't care about what the information is about particle 2. Now, just to be clear, this doesn't answer the question that's above there. If you have this function, there's no question that the two-particle system is in a definite state. This is the definite state, and so the two-particle system has a definite state. The question we're asking here is, does it make any sense to individually ask if one of the particular particles is in a particular state? In other words, we got 2 electrons in a hydrogen atom potential. And does it make any sense to say, where is the 1 electron? Is it in a particular kind of state? We'll be connecting with that later on. The only reason it did make sense in this case was because our wave function had a special product kind of form. In other words, this general function of R1 and R2 happened to be a product of a function of R1 and a function of R2. That's clearly not generally going to happen. That's only very special kinds of functions of multiple variables that are products of the functions of the individual variables. And what that means is, if we calculate what the probability density function, which is just the magnitude of that full psi squared, it factors into a product of individual probability density functions. And it's those individual probability density functions that we're associating with particle 1 and particle 2. So we would say that in this special case where it's a product function, it makes sense to say, oh, you know, particle 1 is in a particular state because it's most likely to be here and it's least likely to be in some other place. There's separate probability densities we can associate with them. In general, that's not going to be true. If psi is not of a product form like that, product of a function of the 1 variables and a function of the 2 variables, we can't say that it's in a particular state. And the example is that I want you to work through is problem 2, which looks very similar, except that notice the function in problem 1 was of a product form. The function in problem 2 is not of the form of a product. It's a form of a sum of a product, but it's actually not an overall product. Notice that all I've done between the first term and the second term in parentheses is switch the x1 and x2 variables, right? So I've got an x1 minus 2 squared and an x2 plus 2 squared in the first one, and I've got an x2 minus 2 squared and an x1 plus 2 squared in the second term. So I've just switched where the variables are located. I want you to think about, it's more complicated. Think about what psi looks like there, where it's most positive, where it's most likely, you know, what regions of the x1, x2 plane that we're most likely to find particles 1 and 2. And then think about the associated probability density. Again, the probability density is not going to be too much different in this case, but there will be other cases where it will be quite a bit different.
Oh dear. Okay.
And especially think about how the answers in part C might change here. Because I think most people's intuition is that the answers ought to always go like they are in problem 1, but how they go in problem 2C is much more generic for multi-particle systems. Okay, so looking at the form on the board that I've got written here, I sort of unfortunately ran a little bit into my diagram, but I don't think it'll matter. We've got the previous function, which we know places sort of a two-dimensional Gaussian hilltop right here, but we've also got added onto it another term, which is maximal where x1 is -2 and x2 is +2. So it's got the top of the hill here and some level curves that are going to smaller values there. Right, and if you got some intuition about level curves, it might sort of go like that. So overall, because nothing's negative here, I don't have to worry about minus signs. I'm just adding a Gaussian on top of another Gaussian that's sort of well separated from it. And it's just like we've added together two hilltop functions. So they go down a little bit in the middle and go up over here and then asymptotically go to 0 otherwise. I'll show you a 3D picture of that shortly. And of course, rho doesn't look terribly different from it. So it's going to also have peaks over here and the same kind of structure. It is a different function, but it has the same general kind of areas of maxima and minima. What about the answers to questions in C? Near which value is particle 1 most likely to be found? Well, you might say, generically speaking, particle 1 is associated with x1, and the function sort of, this two-dimensional function kind of has a maximum near x equals -2 and x equals +2, right? And it goes down a little bit in the middle. Okay, so it's most likely to be found near x2, x equals 2 and x equals -2. Does the answer to the question depend on where particle 2 is found? In other words, so if I say, where is particle 1 most likely to be found? You might say, well, okay, there's a Gaussian peak here and a Gaussian peak here. It's very likely to be found near x1 equals -2 and x2 equals -2. And again, it's the same x for both particles, right? There's only one x, but we're trying to keep track of which one refers to which particle. So we're just talking about one x-axis. Here's 0, here's 2, and here's -2. And you said, I've got to place some bets. I'm going to say, well, I'm going to bet that it's either going to be, particle 1 is either going to be found near there or near there, probably not much in the middle, and certainly very small way up here, right? Because probability density is low down there. The second question asks, does the answer depend on where particle 2 is found? In other words, suppose I say particle 2 is found near x equals -2. Would that affect how you would bet on where particle 1 is most likely to be found? Yeah, it certainly would. If we measure particle 2 somewhere in the vicinity, I can't remember what I said, in the vicinity of -2, if I know x2 has this value, then x1 certainly is very likely to be at +2, right? And vice versa if I measure it in the other location for x2. So the two states affect each other. In other words, the outcome of one measurement affects the outcome of the other measurement, which is also to say that I can't say that the particle itself is localized near x equals 2 or x equals -2 or both. It's that it depends on the state of where particle 2 is. Particle 1's location depends on where particle 2 is found and vice versa. Does the location where particle 1 is found affect where particle 2 is most likely to be found? Yes, it does. If you know the outcome of one measurement, that affects the outcome of your other measurement. That phenomenon of not being able to say kind of what state that one particle is in without knowing what state the other particle is in is called entanglement, generally, for a two-particle system or a multi-particle system. You need to know what the other particle is doing in order to know what the one particle is doing. Okay, any more questions about problem 2 before we talk about it in more generality? I'm trying to get us to draw pictures quite a bit because these two state wave functions are kind of unfamiliar to most people. Okay, so here's another example, maybe more extreme than the Gaussian functions. I'm specifying some functions of x, y, and z. And so these might be states that I would say, oh, a single particle might be in this state if I were ignoring the second particle, right? And this state's kind of extreme. It is only non-zero where all of the 3 x, y, and z coordinates are between 0 and 1. Everywhere else it's 0. So that's kind of an extreme case where I definitely know exactly where a particle in that state is localized. Here's another state that a single particle could be in. This one is only non-zero where the particle coordinates are between 3 and 4. So notice there's no overlap between these two kinds of states here. So in the manner of problem 1 that we were doing, if we take a product of these two states, in other words, we say particle 1 is in state A and particle 2 is in state B. And the way we would describe that with an overall wave function, which is a function of R1 and R2, is to write it as a product of psi A, as a function of R1, and psi B as a function of R2. Particle 1 is in state A and particle 2 is in state B. And in that case, of course, it makes sense to say those words. So if we have a state like this, it makes sense to say particle 1 is in this state, particle 2 is in that state. In the case where we're looking at a wave function that's not a simple product like that, does it make sense to say whether particle 1 is in state A or state B when it's not in a product form? And the answer is no. So if I'm given two states, here's a description of one state. It's a very extreme state that goes immediately to 0 outside a tiny region. Here's another one. The two depend on each other. I could say particle 1 is in state A if and only if particle 2 is in state B. And particle 1 is in state B if and only if particle 2 is in state A. So it doesn't make any sense if you don't have a product form for your wave function to say that an individual particle is in a particular state. And that's difficult because we're used to, even in quantum mechanics, right? We're thinking, okay, one of the electrons is in the ground state and one of them's in the first excited state. But generally, you have to be very careful with that kind of language because in a lot of cases, it's not going to make sense. In particular, for identical particles, because we're going to find, we haven't talked about identical yet, but we're going to find out for identical bosons, our wave functions have to have this kind of form right here. And so they're not allowed to be in a product form. And so we can never talk about one of the particles being in one state and another one being in another state.
Question.
Yes.
Well, so I already understand that in terms of memorization, but what's the logic behind the fact that they have to be that way?
Are you saying why bosons have to be in states that look like that second version here?
Yes. Well, I mean, in contrast to fermions, how bosons are always symmetric.
Oh yeah, well, we'll talk about that. We haven't gotten there yet. I'm just sort of alluding to that in the future. We'll get there.
Very well.
Okay, so again, the term for this where we can't say that one of the two particles, and here I'm generically thinking of the two particles might be distinguishable particles. It's like an electron and a proton. Let's not worry about indistinguishable cases for the time being. Let's just say we know which one is which. We want to know where we're going to find the proton, where we're going to find the electron. In this case, you know, if it's in a product state, we could say the electrons definitely with coordinates between 0 and 1, and the protons would definitely in coordinates with between 3 and 4 if it were in this state. But we can't make any statements like that when it's not of a product form. Okay, and that's what in general we call an entangled state. The two particles are entangled with each other. We've already seen this in the example with describing spins of two particles when we were thinking about combining them earlier. We had states where we would say, well, let's suppose we have two spin 1/2 particles. So let's assume they're non-identical just for this to make it conceptually easier. So an electron and a proton, they're both spin 1/2 particles, right? And for particle 1, maybe we'll call that the electron. I can say it's if I have a state where particle 1 is in a definite spin z state, then I can either write it as an arrow up or an arrow down like Griffiths does, right? And maybe with our particularly chosen z-axis, the electrons in a spin up state and the protons in a spin down state. If you write down a state that looks like this, while this is a perfectly good description of the pair of spins, in the same way, it doesn't make any sense to say, oh, what spin state is the electron in? That's the first of these two descriptions. I'm sort of at a loss for words how to do that. Well, let's say, if you tell me what the spin state of the proton is, I can tell you what the spin state of the electron is. That's what would result after a measurement. But before we make a measurement, I can't say it's in spin up or spin down. It's just the whole system is in a linear combination of up, down, and down, up. But the electron by itself isn't in a particular kind of spin state. So the two spin states are entangled with each other. Now we're talking about spatial description states that can be entangled with each other. And of course, entangled is the generic kind of situation. This state by itself, just this one, is not an entangled state, right? I can say, oh, the electron's definitely in a spin up state and the proton's definitely in a spin down state. But generically, it's not of a product kind of form. And that means that you can't separately describe the particles. That doesn't sort of agree with our way we tend to want to use language. Every time I click on this, it loses contact with my clicker. Okay, let's make the connection with bosons and fermions. So in general, this more general state, not worrying about exactly whether it's a product form or not a product form, This, just like psi as a function, for a single particle state, psi of x could have any normalizable form. The same way here, the generic state, psi of, the particle 1 variables, particle 2 variables at time t equals 0, we could give that any function of those 6 variables that we like, as long as it's normalizable. Right? It can't be the 0 function, and it can't be non-normalizable because it's so infinite everywhere, infinite area under the curve when we take the magnitude squared of it. Now, in the case where we're talking about identical particles, like 2 electrons, then if we allow all this freedom, any kind of normalizable function here, we're going to find that there's something that doesn't seem right for the description of 2 absolutely identical electrons or identical protons. Let's suppose, again, just to simplify, let's just imagine that these electrons are living in one dimension, so I don't have to look at so many variables, right? And so as a function on the x-axis, the electron 1 is very likely to be near x equals a, and electron 2 is very likely to be near x equals b, right? Those Gaussian functions look like that. So here are the 2 Gaussian functions that look like this. Those are, I'm sorry, I didn't mean electron 1 and electron 2. What I mean is these are definite single particle states. So here's one state that an electron could be in. Here's another state that an electron could be in. And now let's consider putting these electrons into 2 different kinds of states. So here's one particular state, and the notation here gets a little bit confusing, but I'm just going to choose to label this definite state as psi 2. Why is it? So it's defined as this particular psi as a function of x1 and x2, which is to say particle 1 is in state A and particle 2 is in state B. Okay, and I'm just going to say, because I put the 1 in the first factor and the 2 in the second factor, that's why I'm labeling this as 1, 2 there. Here's another state. I'm going to call this one psi 1. And that is, I put the x2 variable in the first factor, that psi a factor, and in the x1 in the psi b factor. So, right, I'm saying in one case, particle 1 was likely to be here and particle 2 is likely to be here, and vice versa for the second state. And now let's consider the probability densities associated with each state. So this is just repeated up here at the top, what we just wrote down so that we can refer to it. And let's calculate the associated probability densities. Well, they're actually quite distinct probability densities. As a function of x1 and x2, the magnitude of psi 2 squared is largest in this region of the plane, right? And psi 1 seems to be largest here. But notice, if they're absolutely identical electrons, say, there's no way for me to tell which electron is in state A and which electron is in state B. And so there's fundamentally no experimental way to distinguish between these 2 outcomes, even though our rows we're getting associated with variables x1 and x2 seem to be totally different. One is maximum here and the other one's maximum here. I'm not drawing one function. I'm saying there's 2 separate functions with 2 separate peak locations there. Okay, so experimentally, those 2 situations, even though it seems like, oh, I've got 2 different, totally distinguishable, at least on paper, wave functions, totally distinguishable rows associated with them, and yet I can't tell the difference between them experimentally. Okay, we're never going to know if the electron we measured is electron 1 or electron 2. So we won't be able to know the difference between those. So the question that's being raised here is, should we really consider the 2 states, psi 2 and psi 1, as separate states if they're fundamentally, experimentally indistinguishable? In other words, we're never going to be able to tell any difference between them if the electrons are fundamentally identical. If there's no way to label electrons and follow them around and know which one was electron 1 and which one's electron 2. And my answer is, well, it seems like the answer should be no. But in our theory so far, they are being treated as separate states, right? They have different probability densities. They have different functional forms, right, with different maxima and different locations. despite being experimentally identical. So what we're going to do now is add something to the theory to try to make it so that these kind of states, which are experimentally indistinguishable for identical particles, aren't going to be allowed. And the only ones that will be allowed are ones where it doesn't matter which electron you measure in which location, it looks exactly the same. There's a certain kind of symmetry. Okay, so we're going to place an additional constraint on these functions. We're not going to allow it to have any normalizable form. We're going to place an additional restriction. And the restriction is usually phrased in terms of something, there's an advantage to introducing a new operator. We're going to call this operator the exchange operator. In Griffiths, I believe it's written as a script P, which I know looks like momentum, but you'll be able to tell when you see it in Griffiths. It's got this fancy script form. And the P, I think, is for permute. When you permute things, that means you switch the locations of them. So here we're permuting the variables x1 and x2. So the exchange operator, which is going to help us define the allowed states, is that if you give me at time t equals 0 a function of R1 and R2, the exchange operator applied to it just switches where the R2 and the R1 are in that function. So in other words, if, just to give an example, because I don't think I have one written there. I know this is a little bit of a mess there. Forget about this stuff over here. If this were my function of x1 and x2, if I applied p to it, the permute operator, or what's called the exchange operator in Griffiths, I would get this function over here. I just switch the locations of the x1 and x2 in there. So it's pretty simple. It's not doing a whole lot, but we're going to phrase the allowed, oops, that's not what I want to do. We're going to phrase the allowed states in terms of that operator after a little bit of investigating the operator. Okay, so or maybe not. Here's what I'm going to say. We demand, or in other words, this is a new postulate that we're going to add to our postulates in quantum mechanics, because we haven't been describing multiple particles, certainly not identical particles so far here. If we have identical particle states, we demand that they're going to be eigenfunctions of this permutation or exchange operator, where we exchange the positions in the function of the two variables. And because I guess I didn't say it in here, but because I'm going to define psi of R1, R2 to just be psi of 1, 2, right? This just means the one variable, and this means the two variables, because you'll get so tired of writing those vector R1 subscript variables and all that. So I'm going to write them as psi 1, 2, and when we permute it, we get psi 2, 1. You got to remember that those ones and twos represents variables. So we're going to demand that whatever our wave function is for two identical electrons or two identical protons or any two absolutely identical particles, that when you apply this exchange operator to it, you get a multiple of the same state back. And when you get a multiple of the same state back, that says when you apply the exchange operator, something really trivial happens to it, right? Because if you get a multiple of the same state back, that means the probability density is going to be unchanged, right? If you just say, hey, take a state and multiply it by 2, well, that just changes the normalization, and then you renormalize it, and you get the same exact thing back again, right? So that's saying the allowed states, when you apply P, are changed only in a trivial way that doesn't affect the experimental probability densities. If you're in one of these states that is defined by changing the variables, you better get a multiple of the same thing back again, and then the probability density is going to be the same, and then we won't have this problem of two distinct, right? The whole problem with the one that I pointed out before was that psi with the one variables first and the two variables second was totally different as a function of x1 and x2 for the two first and the one second. But here, we're supposed to get the same probability density as a function of x1 and x2. Generically, that's what this for other states. If we're not in one of these allowed states that is an eigenfunction of the exchange operator, applying this permutation or exchange operator drastically changes the state, and it changes the probability density. So we're talking about very special states here, and we need to figure out what those states are, which of course is going to lead towards the answer to Elvis's question. But first we need to develop some of the properties of the exchange operator. One of the most important thing is that the eigenvalues, so we're looking for eigenfunctions of this operator. The eigenvalues are plus or minus 1. Anybody have an idea of how we might prove that without looking down at your notes? Since it is in the notes. You know, this exchange operator is pretty simple in that it just switches the positions of the variables in the function. And so if you apply it twice, it doesn't do anything. Okay, so I'm going to try to draw a script P as best I can. I want to find the solutions to this. P on, okay, this means x1 is in the first position and x2 is in the second position. It's just me being lazy and not wanting to write it. I can't remember, maybe Griffiths even is lazy in the book. And that's equal to lambda times psi of x1 and x2. So this is the eigenvalue equation. It's going to determine both what the eigenvalues are and what the eigenfunctions are by sort of thinking about that. And the interesting thing is that if I apply the permutation operator again to this, right? If the permutation operator operating on it once gives a lambda out in front, the permutation operator or exchange operator applied to psi1, 2 twice in a row certainly gives 2 factors of lambda out in front. But notice that when you exchange them and then exchange them again, you get the same thing back again. So this is psi of 1, 2 back again. I've switched them and switched them again. So applying it twice in a row doesn't do anything. And so if these two sides are going to be equal, and this is a perfectly normalizable function, a non-zero function, that means that lambda squared has to be 1. And that means that lambda is equal to plus or minus 1. That's an easy proof that those eigenvalues are pretty simple to get. Questions about that? Okay. So there's the proof. It's in the notes. Easy enough. Here's another interesting factoid that it's unclear why we want to know it now, but it's one of the reasons that we introduced a formal operator to show that something is true. You can also show, and I'm not going to prove it right here in class, that the commutator between the exchange operator and the Hamiltonian is 0 for identical particle systems. And I put it in micro font here because I'm not going to talk about it in class. It's a straightforward kind of proof, but not very interesting. Why do we want to know that? Well, it'll show up on the next slide. So just keep that in mind. The exchange operator commutes with the Hamiltonian for identical particle systems. Okay? So all I've done is put in the appropriate eigenvalue into the statement we had before. The eigenvalues are plus or minus. Okay, so that means when we switch the order, we get plus or minus the original function coming back again. Here's the important thing for thinking about bosons and fermions. So this is based on something that we didn't talk about back in the section on the generalized uncertainty principle, where we talked about the energy time uncertainty. If an operator commutes with the Hamiltonian, in this particular case, we can conclude that the expectation value of that operator doesn't change with time. Where did that come from? That came from a theorem that was in Griffiths. You probably breezed by it, but here is the generalized Ehrenfest theorem that was in that section on the energy time uncertainty relation. There's a lot in that section, and we just didn't talk about it, but it tells us what the time rate of change of the expectation value of a generic operator is. And it's written as 2 things. One involves the commutator of that operator with the Hamiltonian. So in our case, this is 0. And the other one tells about the expectation value of the partial derivative of the operator with respect to time. And all the operators we've ever dealt with in this course have been independent of time. Now, the one exception would be our Hamiltonian could actually have explicit time dependence in it. In other words, it depends on the variable t when you write it out explicitly in terms of its variables. But the momentum operator doesn't explicitly depend on t. It's the same at every time. And it's the same way with this exchange operator. It doesn't have any explicit time dependence, so its partial derivative with respect to t is 0. So this term is also 0 for the exchange operator. Oh, and I see I've got to stop, so this is the place where we'll stop here. And what that means is that the left-hand side is 0. The time rate of change of the expectation value of the exchange operator is 0. And what that means is, you have to kind of think about this for a second. That means that states, so our two allowed states, since we're demanding that identical particles be eigenstates, the ones with a minus eigenvalue at time t equals 0 maintain that minus eigenvalue because the expectation value of that exchange operator is going to be -1. Once it's -1 at t equals 0, it's -1 at all later times. And that means we can sort of say it's an inherent property of the particle. It's not just happenstance that it happens to have -1 at this particular time. Once it has an eigenvalue of -1, it always has an eigenvalue of -1. And it's the same thing for eigenvalues of +1. And therefore, we're going to give the name bosons to particles that have that exchange operator of +1 and fermions that have the exchange operator eigenvalue of -1.